This top trace is, as usual, the signal from the function generator. I'm using the function generator for this demonstration because it can do things that the 555 timer cannot do, and I want to illustrate that. So this is the trace from the function generator at 5 volts per division. Sorry, it's this one here. We're using a 10x attenuated probe, so the volts per division figure is 10 times that. So we're at 5 volts per division on this trace, which is the trace from the function generator. This trace is the common MOSFET drains, which is taken at the transistor side, the drain side of the load, and you can see that it has the oscillations on there, and that's being shown at 50 volts per division, and you can see that the baseline level is there, and we're showing 50 volts plus the oscillations, and the magnitude of the oscillations is about 60 or 70 volts peak to peak. Okay, and so we're showing the battery voltage there. Now, this is the common MOSFET drains, but I can just as easily just take that probe off of there and move it over to the battery positive lead, right? And you see the same oscillations. There's the battery positive, there's off, there's the common MOSFET drains, there's the battery, okay? The reason I show the common MOSFET drains is because it gives more information about what the circuit is doing than the battery does. In fact, it gives critical information about what the circuit is doing, and that's why it has been omitted from certain other scope traces from other people who are working with this particular circuit. Alright, so we have the common MOSFET drains and the function generator output there. Now you'll notice that the function generator output is going negative, right? There's the baseline 0 voltage level, there's the negative going pulse, and we have the function generator set to produce a negative going pulse, and sure enough that's what it's doing. Now we're triggering on the output of the function generator directly into the scope's external trigger so that our manipulations here won't affect the triggering, hopefully. Okay, now before I lose the thread of the demonstration, what I want to do here is demonstrate how the oscillations and MOSFETs turning on can be determined from the drain trace as we vary the offset of the function generator. Okay, so right now we're seeing oscillations in the Q2 stack, right? We've determined that that's the case, and the battery voltage is at this baseline level is at the battery voltage, so no MOSFETs are actually switching on, especially not during this time. They may be partially on during the oscillations, but that remains to be seen. And they must be partially on during the oscillations because the load in fact does heat during this mode. Okay, so at any rate, now what I'm going to do is just vary the offset to raise this the driving pulse to a positive value. Okay, so here we go, up, 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 up. Now you'll notice that the bottom of that trace doesn't move yet as I go up. That's because we're experiencing this voltage floor that .99 has noticed in the simulations and that I've noticed in the real build, and that still is kind of unaccounted for. At any rate, it's real. The negative voltage will not go below that, but as I go positive, you can see that the oscillations shrink and shrink until at this point right there, the Q1 MOSFET is beginning to be partially turned on by the positive going gate drive pulse. You can see that this line has dropped below the neutral 0 volts line. So that means that voltage on the common MOSFET drains at this point is dropped below battery voltage, which means that the MOSFET is on. And sure enough, that's reflected in the current reading through the circuit, right? Just as soon as that little trace drops from the adjustment of the offset, just as soon as it drops off of that level right there, boom, the current goes up from its quiescent value, boom, to that partially on MOSFET value. Okay. Now, if I make the drive even more, but notice that you still see the oscillations there. Okay. Now, this is what Ainslie has shown: positive going gate drive pulse, but enough negative to actually cause the oscillations to still occur. You need that negative bias on the Q2 stack for the oscillations to occur. If you don't have that little negative bias, they won't happen. And as I go further and further up with the function generator offset, you'll see that the oscillations disappear, and then the MOSFETs are turning cleanly on, or rather the Q1 is, right? Because the voltage on the drain is right down now at, or close to, focus, the 0 level. So I'm going to go back down with the offset, and you'll see that it hits that voltage floor and then drops on down until we have now once again a strictly negative going, an apparently strictly going negative. And here we have apparently strictly going positive, but not really, because we're still providing some current to the Q2 stack, even though it looks like we're at that 0 drive level on the function generator trace. But we know we're providing current to the Q2 stack because otherwise it wouldn't be oscillating. Alright, now let me go back to this mode right here, and let me reduce the amplitude of the current of the function generator. Okay, so I'm reducing the amplitude now until let me crank that up a little bit. Okay, so I'm playing with the amplitude until I get a true 5 volts peak-to-peak signal there. Now I'm going to lower it down until it's all negative going. No problem here, we have the oscillations, right? But now I'm going to raise it up until it starts going positive. Look, no oscillations, right? That's because now we really aren't giving the Q2 stack any bias current, negative bias current, that makes it oscillate. Alright, so with a true 5 volt peak-to-peak driving pulse, if you go negative, you hit that voltage floor and you produce the oscillations. If you go positive, you simply turn a MOSFET on, the Q1 MOSFET on. Right? But you don't get oscillations. If, however, you increase the amplitude of the function generator's output, simply increase the amplitude, now you can go to what appears to be an all positive looking drive, but you still get oscillations. Okay? You see what's happening? This looks like it doesn't have any negative component, but it does, because you're making oscillations. If again I reduce the drive, reduce the amplitude, you can see those oscillations going away, but there's apparently no or very little change in what this trace looks like, right? High amplitude, low amplitude, right to there, but it still looks like there's no negative going pulsations. However, if I turn the amplitude down low enough so that you really do just have 5 volts peak to peak there, then I can raise it up, positive offset, no oscillations, lower it down, oscillations. Okay, so does this make any sense? It makes perfect sense to me, but I know that there's somebody that it won't make sense to. Thank you for watching.